Okay, so today I'm going to wrap up chapter 9, which we are discussing alkynes. And so in the previous lecture, I went over to name alkynes properly. And then we started talking about how to synthesize them through those elimination reactions, such as dehydrohalogenation, which remember I'm going to go into more detail in chapter 11 when I go over E1 and E2 type mechanisms. And we then went on to talk about like the hydration of alkynes, so adding alcohols, which then those enols automerize into the ketones, either like an aldehyde or a methyl ketone. So we're talking about those different reactions of alkynes, and it's very similar to alkene reactions. There are some more limitations to alkynes than there are to alkenes, and you've seen that already with the hydration reactions. You prefer to have a terminal alkyne rather than an internal alkyne, which would give you a mixture of products. So today I'm going to continue on talking about those reactions, and then I'm going to wrap up this chapter discussing multi-step synthesis. So from here on out, you as an organic chemist, as a beginning organic chemist, is going to be able to synthesize a variety of molecules from starting material. And that's the goal. That's what I'm teaching you. It's these critical thinking skills of how you would synthesize it, knowing all these reactions. So like I said before, once you've learned these reactions, don't forget them because we're going to use them over and over and over when we do multi-step synthesis. Okay? So the first thing I wanted to cover today is talking about the reduction of alkynes. Remember, reduction essentially means in organic chemistry that we're adding hydrogen, right, to a compound and therefore gaining electron density at that carbon center. And so before, with alkenes, it's very analogous. So we add hydrogen and a palladium catalyst or platinum catalyst, and the alkenes convert it to their alkanes, right? And so that was very simple. You've done that already. If we do the same type of reaction with alkynes, using hydrogen over palladium on carbon, for example, once again, it takes alkynes all the way to alkanes. It's a complete reduction. We don't stop at the alkenes, okay? Knowing that we have, there's so many reactions for alkenes, we'd want to have a way to stop at an alkene and not have to reduce completely to an alkane. So there are reactions that are able for us to do that. I'm going to talk about that in the next couple of slides. But first, I just wanted to show you that the first addition of a hydrogen gas should have produced this alkene here. And it will, but that second addition of that particular hydrogen with that catalyst will take it all the way to the alkane. Okay, and so these are very exothermic, favorable reactions. They release energy, hence the negative sign. So how would we convert it just to an alkene? Well, one way is to use hydrogen gas still, like we did before, but use a deactivated catalyst. Okay? So we're going to use a deactive palladium on a calcium carbonate as the catalyst. And I'll just have you refer to that particular catalyst as Lindlar's catalyst. And it's important that you understand and you remember that Lindlar's catalyst helps to produce a cis alkene. Okay? Cis only, not trans. Because you're working on a catalyst, you still have a heterogeneous reaction mechanism. And remember when we talked about this in chapter 8, that's like a stamping mechanism, right? So the hydrogens have to add to the same side or syn addition. And that's why we get cis stereochemistry. So we add hydrogen, Lindlar's catalyst, that helps us to stop at the cis structure there, the alkene. We could go on to take it all the way to the alkane if we needed it to, right? So you have some flexibility here, some versatility, which is good. It's a reaction that they use in the industry to convert this starting material here or the precursor to this product, using hydrogen Lindlar's catalyst to make 7-cis-retinol. Okay. Now you may be wondering, well, how would I make a transalkene? Instead of a cis, because stereochemistry is obviously important. I may need a transalkene instead. And so to do that, we use anhydrous ammonia, and at negative 33 degrees Celsius, very cold temperatures, and an alkali metal. Alkali meaning group 1A. Many cases we see lithium as our group 1A metal. You may see sodium. It just has to be a group 1A metal that's willing to donate an electron. And alkynes are reduced to the transalkenes, like I said, with sodium or lithium and liquid ammonia. And this reaction mechanism involves a radical anion intermediate, which sounds really crazy, and it is. I'm going to show you the mechanism on the next slide. But for right now, you can just see how we can go from this 5-decyne to now a trans 5-decene. Okay? Pretty high yield, 78% yield. So it's a pretty high yielding reaction. So I wanted to go through the mechanism, and it is one of the craziest mechanisms you'll see in my class because it involves this radical anion intermediate. But I wanted to show you it so you can see why we have trans stereochemistry and not cis. So I'm going to start with a simple internal alkyne. And I'm going to have lithium here. And lithium has how many valence electrons? 1 valence electron. And how many electrons does it need to give away in order to be like a noble gas configuration? It wants to give away 1. So it's desperate to give away 1. So what ends up happening is that 2 electrons move over and are localized onto that carbon atom, while the other electron that's donated moves on the other carbon atom. So the result that you get so 1, 2, 3, 4, 5, 6. 3, 4, 5, 6 is that you get this anion here, which is a -1, because that's carbon's got 3 bonds and a lone pair. And then you're left with a radical here on this other side of the double bond. So that's why this is called a radical anion intermediate. Okay, so now what happens is that, remember, we added lithium, but we also added ammonia. Oh, and at the same time, I should show that. Byproduct is lithium plus 1. So like lithium's happy now, right? So it's in its noble gas configuration. So we also have ammonia in solution. And that anion is just so desperate for protons, right? So it's going to grab off a proton off of that ammonia molecule, even though usually ammonia is not a good acid, right? You're like, it's more of a basic compound, right? But because that anion is just like, I just want a proton, it's going to grab it from the hydrogen off of the ammonia. So we have a hydrogen here, and we still have that radical here. So we have a radical intermediate here. And we create NH2, so it makes a very basic solution. When you do this reaction, you gotta be careful. And we still have lots of lithium left over. And so what happens next is that lithium is willing to donate another electron. Now we're going to make an anion here. So we make this anion intermediate, and this anion intermediate prefers to be, in a trans, this vanillic anion prefers to be in a trans particular stereochemistry rather than cis, because it'd be just too congested. So everything spreads out into a trans stereochemistry. And then once again, the next step is that there's more ammonia in solution. So therefore, this lone pair of electrons pulls off this hydrogen, put those electrons onto the nitrogen. And we end up with a transalkene plus more of the NH2. I'm sorry, guys. 1 second. My pen's not calibrated very well today. There we go. And a -1 formal charge. So basic solution, very basic. Okay. So make sure you practice that mechanism and understand that a lithium and ammonia or sodium ammonia give you trans stereochemistry. So it is a stereoselective reaction. Remember that the chunky arrows that are going backwards resemble something for retrosynthesis. Once again, I'm just trying to get you to think backwards. You know, what do I need this to make this product? Because that's what it's going to be really helpful for your multi-step synthesis. And so here, I just covered this material, so you kind of know what you're supposed to do here. But here I noticed that the key functional group I have in my product I want to synthesize is a transalkene, and I know I can do that from a triple bond. And so I'm going to draw the triple bond where the double bond is, and then there's a methyl group here. 1, 2, 3. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Always important that you count your carbons. I make this mistake all the time where I may have not drawn enough carbons, or I may have drawn one too many, so it's good to double check yourself. Okay? What reagents would I need in order to make it into a transalkene? Good. Lithium and ammonia. Excellent. I would have also accepted the sodium and ammonia as well as an answer. Okay? Good. So the next one, we're trying to make a what kind of functional group? A cisalkene. So once again, we know how to do that now from a triple bond. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then what reagents would you use? Hydrogen and Lindlar's catalyst. Good. Awesome. Make sure you practice these. Both of them are going to be very useful in your multi-step synthesis, because in a second I'm going to teach you, not in the next slide, but the next couple of slides, I'm going to teach you a very important reaction. And that reaction is going to help you to grow carbon chains, which will be important, very critical for us to make carbon-carbon bonds. But it grows and makes a triple bond still. And so a lot of times you'll grow something and then you'll reduce it to a double bond and then do some really neat double bond reactions to it. Okay? So these reduction reactions are very popular, okay, for that reason. I wanted to go over oxidative cleavage of alkynes. For alkenes, it was really useful to do oxidative cleavage. And you can do the same thing with alkynes. And no matter if it's ozone or potassium permanganate, alkynes will oxidize all the way to carboxylic acids, no matter what. So it's not like alkenes in a sense where we stopped at the aldehyde for ozone. Okay, for alkynes, we do go all the way to carboxylic acid no matter what. And we don't really use these particular reactions for our synthesis. So if anyone uses it, it's mainly just to identify, okay, I made these products, so what exactly was my precursor? So to work backwards to determine what alkyne they have. So not a very useful reaction. If you're going to do oxidative cleavage, then you're probably going to want to reduce to a double bond first and then do those particular reactions so that you get better yields. And You can get aldehydes versus carboxylic acids in that, depending on what reagents you use. You just don't have that flexibility with alkynes. Okay. Now I wanted to move on to talk about alkyne acidity and the formation of the acetylide anion. Terminal alkynes are actually weak Bronsted acids. And if we look at the pKa data, remember the smaller the pKa, the stronger the acid. And so when we look at the data of an alkyne versus an alkene versus an alkane, we'll see that alkynes in comparison are the stronger of the acids. I mean, a pKa of 25 is still a very, very weak acid. So we'll need an extremely strong base to pull off that proton, but it does say that it could happen, right? And so we use that to our advantage. Like I said, terminal alkynes are weak Bronsted acids. We need a strong anhydrous base. Remember, anhydrous means just without water. With a terminal acetylene to produce what's called the acetylide anion. You need to know that word. You need to be able to say it and spell it properly. Okay? You can't use sodium hydroxide here. The best ingredient to use is sodium amine. And this is what's going to be eventually called the sodium amide coupling. So what happens is that these electrons pull off this proton, and these electrons go onto this carbon. You make ammonia, and you have the acetylide anion. Okay? Very easy, very simple reaction. Now I want to explain these structure-property relationships because many times students don't understand, well, why the acetylide ion? Like, why that is made, not, for example, an anion on a double bond or on an alkane, for example. Excuse me. Why is the acetylide anion more acidic? And the reason why that proton or acetylene is more acidic is because when we pull off these protons, I've drawn the anions here in your figure. I've put that there, right? And if we look at the hybridization of this carbon atom, you would tell me it is sp. For the vanillic one, you would tell me it's sp2. And for the alkyl anion, you would tell me it is sp3, right? And we know that s orbitals are spherical and that p orbitals have this dumbbell shape, right? But where do you think electrons want to be? They want to be closest to the nucleus. And if a p orbital is a dumbbell shape, it has that node, right? So p orbitals, remember, have two lobes and a node around the nucleus, right? Well, if we look at the hybridization of these atoms here, this one that has sp hybridization has more s character, more spherical-like character. So that particular orbital those electrons will want to be there because they'll be closer to the nucleus. Whereas on the other hand, for an alkyl anion, for sp3, it's only 25% s. So it's mostly p character, and that means those electrons are not as close to the nucleus as they like to be. And so therefore you can see that this one has to be more stable. Remember, the strength of the acid is determined by the stability of the conjugate base. So it's important that you know that. Remember, we went over that over and over again when we did the acids and bases chapter. I talked about how if you know the stability of the base, right, and this is the conjugate base, then you know the strength of the acid. So because this is a more stable conjugate base, that means its acid is more acidic than the other two. Okay? So that's the reason why we're able to pull off that proton. So I want to go over the actual reaction mechanism. Okay. You'll want to use a terminal alkyne because you have to have a proton, right, to pull off. Right, so I'll have this particular alkyne, and we have a base coming in. So sodium amide breaks up, and we have those amine anions swimming around. And those electrons pull off this proton, and these electrons here are localized onto that carbon atom of the acetylide anion. So let's go ahead and draw we have a lone pair and a -1 formal charge on that carbon atom, and we've also made ammonia. There we go. Okay. Now the second ingredient we have to add is an alkyl halide, and preferably it has to be a primary alkyl halide. So I'm going to draw a primary alkyl halide. So I have propyl bromide here. And that anion is the nucleophile. That alkyl halide is the electrophile. That alkyl, or this acetylide anion, wants to attack this carbon here. Why does it want to attack that carbon? Because it's partial positive, right? It's attached to the bromine. So it attacks the partial positive carbon and then kicks off the bromine because that's a good leaving group. So let's go ahead and see what we've made. And we have a new bond, so I'll draw that in green. And then we've grown it by 3 carbons. So let's double check. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So I drew the correct number of carbons, and it looks like we have grown our starting material by 3 carbons. So you can see how we can use this particular reaction to our advantage, especially in multi-step synthesis when we're trying to synthesize from small starting material and then grow. Okay? Now I just wanted to emphasize here that this can only work, oh yeah, I'll just show this here real quick. But this can only work with primary alkyl halides. So for example here, this was a primary alkyl halide because this carbon is only attached to one other carbon. Okay? So sterics plays a big role in this mechanism, and that's the one drawback to it. It's kind of like the exception to the rule. So when you're making your table of reactions, you know, you always want to write down exceptions or things that you have to, like, okay, be aware of. I cannot do a primary, or I can't do a secondary or tertiary alkyl halide. It's not going to work, you know? You want to know all the exceptions to the rules. So acetylide ions can react as nucleophiles as well as bases. We showed that anion reacting as a nucleophile, it attacked the primary alkyl halide. But that means we need a reaction with a primary alkyl halide to produce a hydrocarbon that contains carbons from both partners. And so, like I said, the key here is a primary alkyl halide. Okay? You can always start off with acetylene as your starting material, add 1 equivalent of base, 1 equivalent of the alkyl halide. Or you could do two equivalents and grow out both ends at the same time. Or you could also have a terminal alkyne. It's up to you what your starting material will be and how to be efficient and then cost effective, right? That's the key there. I can't emphasize it enough. The limitation to the alkylation of acetylide anions is that the reactions are only efficient with primary alkyl bromides and alkyl iodides. Even with alkyl chlorides, we don't get very high yields. Acetylide anions can behave as bases as well as nucleophiles, so that's why you have to be careful. If you react with the secondary and tertiary alkyl halide, it actually gives the elimination dehydrohalogenation product, converting the alkyl halide into an alkene. So what happens was it acts as a strong base, it pulls off this proton, these electrons go here, and it kicks off the leaving group, and instead makes the double bond, right? So this is the acetylide anion acting as a base. Okay? All right. So based on this knowledge, we want to think backwards. Pause the video and do this on your own, and then check your work. Okay? What you're trying to do is you're trying to synthesize this product and whatever reagents you need to do that in starting materials. Hopefully you've had a chance to look at it. You've paused the video, you've done the work, and now you're checking your work. So the idea here is we obviously have an internal alkyne, and it looks like I can grow it, or it was grown. So I'm going to make this part the alkyne. It looks like I grew it 1, 2, 3 carbons long. That means that the first step in order to grow this alkyne and make it a terminal alkyne is to react it with sodium amide and ammonia. The second step is to react it with propyl bromide, which is 3 carbons long. Okay? Notice how when I made my alkyne, I made the alkyne sterically hindered so that this part, this alkyl halide, was definitely primary and just not sterically hindered. It's going to make way more sense when I go over chapter 11 with you, why that's the case. For right now, that acetylide anion is a very good nucleophile. We'll see it show up again. Let's see how you did on this one. So I kept the left side once again, this part here as the alkyne, because I knew that there's a lot of sterics involved here and didn't want that to be an issue. So the first step is sodium amide. And the second step, we grew it 2 carbons long, so ethyl bromide. Okay, so just thinking backwards one step at a time. All right, so we're finally at the heart of organic chemistry, and that is organic synthesis. It helps us to create molecules by design. Okay. Synthesis can produce new molecules that are needed as drugs or materials to help solve our world's problems. They can be designed and tested to improve efficiency and safety for making known molecules. So maybe you'll make something that someone else has already made, but you're optimizing the conditions. Highly advanced synthesis is used to test ideas and methods, and it answers challenging questions. And then chemists who are engaged in synthesis may see some of the work as elegant or beautiful when it uses novel ideas or combinations of steps. This is very subjective and not part of the introductory course, and so what I'm saying here is that initially when 12A, you're only going to have maybe 3 or 4 step syntheses on your final exam and on your test. In 12B, we'll increase that number, but there's no way that I'm going to make you do, for example, a 60-step synthesis, multi-step synthesis. That would be too crazy. But, at the same time, if you did come up with one that may be considered to be elegant, for example. So they use words just like that when describing a synthesis. But in order for you to propose a synthesis, you have to be well-versed in your reactions. You have to know them forwards and backwards. You need to know what they begin with, what they lead to, How are they accomplished? What reagents? What conditions do we need? What are the limitations, which is a big one? A synthesis combines a series of proposed steps to go from a defined set of reactants to a specific product. And then questions related to the synthesis can be included as partial information about the reaction of series the student completes. Okay? So how do we do that? And a lot of times when I give multi-step synthesis on tests, some students panic, and then they just don't want to write anything down, and they're just, I don't know it, so they just leave it blank. And that just makes me really sad, because I teach you a lot of strategies to approach these problems, and I want you to write as much down as you can, and hopefully you'll get some partial credit. If you, my apologies, if you hopefully get partial credit if you're on the right track, okay? Can't just write just anything down, okay? It has to make sense, and I have to see where you're going with it. So let's look at this one here. First thing is you always compare your target product and the starting material. And you try to think of reactions that will efficiently produce the outcome. So for example here, we want to synthesize octane from 1-pentyne. Well, it looks like to me I have to grow my carbon chain 3 carbons long. Now right now you only know one carbon-carbon bonding reaction, and that is sodium amide coupling. So that's what we did first. We grew it by 3 carbons long, reacting with propyl bromide to make 4-octane. Now remember, I don't want octane, I want octane. So then it is simple reduction, hydrogen and palladium, and then it got octane. Okay? Simple as that. So let's do the next ones together. Make sure you do know the structure of acetylene. And this one says synthesize 2-bromopentane from acetylene. So first thing you want to do is just draw the product and the reactant. And to me, what's one thing you notice for sure you have to do? We'll definitely need to grow, right? Because we have 2 carbons here, and we have 5 carbons here. So, I usually tell students off to the side, write some notes down. So I would say that we need to grow by 3 carbons. Okay? That's one thing, so that makes me think sodium amide coupling. Another thing is we need a halogen, right? We need a bromine here, and we need a bromine, what looks like could be, how we've made alkyl halides before. By just electrophilic addition, right? And it looks like the bromine, if we had to draw the previous step, it looks like it would have come from an alkene, and that's the more substituted side, right? So, okay, it looks like we might have to use HBr and ether, some sort of electrophilic addition reaction. But before that, maybe I had a triple bond after the growth. 1, 2, 3, 4, 5. So I can see how I can take it one step backwards, and that will help me think of what I need to do forwards. Okay? There's no set way to doing this. Like I said, I think it's important that you say, okay, I highlight this is the most important part. This is just extra work over here. So what can I do to make this? This is an alkyl halide. I know electrophilic addition, right? Right? And then I'm like, oh, well, electrophilic addition to an alkene, I'll have to have an alkene. Before I do that, maybe I'll have a triple bond, right? So I'm hoping that will help to jog your memory. Now, for multi-step synthesis, you do not need to show the mechanism, but you do need to show the reagents and correctly. If they're stepwise, you need to indicate 1 and 2. If it's just all at once, it needs to be indicated as so. Okay? Because right now, this is what organic chemists do. They design their syntheses and they walk in the laboratory and do it, right? So me training you as an organic chemist, will give you that ability to be able to do that if you needed to. So first thing I'm going to do is grow it. So sodium amide, we have ammonia in there, and we're going to grow it by 3 carbons long. Now, I only added one equivalent. I can write that here, one equivalent, just to be careful, one equivalent there. If I did two equivalents, then it would grow on both sides, so that would be dangerous. Not dangerous, it just wouldn't give you the right product. 1, 2, 3, 4, 5. But I know once I have that hydrogen there, it's like a terminal. It looks like I wanted a terminal. It's that one right there. Then what do I need to do to get to an alkene? Good. Maybe you said hydrogens and Lindlers, or you could have done lithium and ammonia. Good. Excellent. And then finally, what's the last step here? HBr and ether to give you the product. Good, excellent. So now I want you to pause the video, and I want you to be able to make butanol, which looks like this, from 4-octine. Okay? Try it on your own. Don't worry, I haven't taught you how to name aldehydes yet, so I don't expect you to know that name and that structure. But if I give you the structure, be able to synthesize it from 4-octine. Okay, let's check your work. So when I see this, and I see that my starting material is longer, I think I need to cleave, right? And I want to make an aldehyde. I know two ways of making aldehydes. I can do hydroboration of a terminal alkyne, or I can do oxidative cleavage with ozonolysis of a symmetrical alkyne, right? Which I think that's the one I'm going to choose. So I'm first going to start with the octine. 3, 4, 5, 6, 7, 8. And I'm going to reduce it. And what reagents are you going to use to reduce? Lithium and ammonia, good. You can also use hydrogen Lindlar's catalyst. 4, 5, 6, 7, 8. Excellent. So I've made my 4-octene now, or octforene. And now I want to use what reagents? Ozone, zinc, and acid. Good. And if you ever see me do, for example, ozone, zinc, and sulfuric acid, remember sulfuric acid is just a strong acid, so essentially that's like donating hydronium ions in solution. Okay? And so that should give you, once you cleave, that will give you the product that you want. Okay. Awesome. Okay. And then one last one. Try it on your own first. I want you to be able to synthesize 2-heptanone. 1, 2, 3, 4, 5, 6, 7. From this from acetylene. Okay. Hopefully you had a chance to work it out, and now you want to check your work. Seems like acetylene we're going to have to grow by 5 carbons, and that's something that I would do first anyways. I also noticed that I have what kind of functional group? I have a methyl ketone. Remember, methyl ketones come from oxymercuriation of what? Terminal alkynes. Good. So it seems like I want to have a terminal alkyne here, right? So I can do my hydration reaction and get it to tautomerize into a methyl ketone. Okay. So let's start off with acetylene. It looks like this. Because I want it terminal, I just want to react it with one equivalent of sodium amide and ammonia, and react it with 1, 2, 3, 4, 5 pentyl bromide. And then I'm going to have 1, 2, 3, 4, 5, 6 7. Excellent. And now I have my terminal alkyne. I just need the reagents to do my oxymercuration. And it's different than alkenes, and make sure you make note of that in your tables or when you're studying. We do need mercury, but we'll use mercury sulfate instead of mercury diacetate. We will need some sulfuric acid and water, and everything's added all at once. It's not like a two-step process. No sodium borohydride needed. Okay? And this is going to give you your 2-heptanone, your methyl ketone. Okay? So really practice these reactions. And something that I like to tell students is like, try to come up with your own multi-step synthesis and then test them on your friends, so in your study group. And I've noticed that study groups who do that and come up with like 4 to 5 step multi-step synthesis and try to trick each other really end up doing very well on my exams and on the national ACS test. Because they've challenged themselves. They didn't just practice the same problems that I've provided on the lectures or in the work sessions or in the textbook. They try to be innovative themselves and think like a chemist and think like the professor. So that's something I challenge you to do. And you can always come to my office hours or bring your test problems to my work session so I can look at them and say, yeah, that's a feasible multi-step synthesis. Hey, maybe I'll borrow that. Just kidding. Well, sometimes I do. Sometimes I use student examples, and that helps. The students get really excited when they come up with good examples and they see them on their test. But, if you do that, that's going to challenge yourselves to think outside the box and to practice different combinations of different reactions. Okay? So make sure you read through the textbook. Make sure you watch through the lectures all the way through and maybe once more again. Practice your reactions, practice the work sessions, and I'll see you in class. Ask lots of questions. I'll see you soon. Good luck studying.